All right, we're diving into something pretty fascinating today. We're going to flip through a field technician's actual lab notebook to get a look at the hidden chemistry behind one of the most important materials in the energy industry. You might think it's just mud, but trust me, it's a super high-tech fluid. And these notes, well, they're going to be our guide.
So when you picture drilling for oil, what comes to mind? Probably these giant, massive rigs, powerful drills, right? And yeah, you're not wrong. But the real secret to punching a hole thousands of feet into the earth, it's not just about brute force.
Turns out, the unsung hero of this whole operation is a substance that looks, kind of simple, but it's actually incredibly complex. I'm talking about drilling fluid, or as everyone in the industry calls it, drilling mud. This stuff has three really critical jobs. First, it's got to cool and lubricate that drill bit while it's just chewing through solid rock. Second, it has to carry all those little rock fragments, they're called cuttings, all the way back up to the surface. And third, and this one is absolutely crucial, its weight creates this downward pressure that has to fight the immense upward pressure from the oil and gas down there, which is what prevents a catastrophic blowout.
Okay, so here's our game plan. We're really trying to answer one big question. Why is every single ingredient tested so rigorously? We'll start with the foundation, the water and clay. Then we'll see how they control all that pressure with weight. After that, we'll get into the really cool stuff, the power of polymer additives. And finally, we'll see how it all comes together when we're putting the recipe together.
You know, every great recipe, whether you're baking a cake or engineering a fluid like this, it all starts with quality base ingredients. So for drilling mud, that means we have to start with the two most basic components, clean water and a very special kind of clay.
But how do you make sure the water is clean enough? We're not just talking about, dirt or something you can see. We're talking about invisible, dissolved minerals and ions that can completely mess up the chemistry of the whole batch.
And check this out. These notes, pulled right from the source, show us the exact process. A chemist is testing for calcium and magnesium ions. See, these little guys are unwanted guests. They can interfere with the other additives we'll put in later, so they have to be measured and accounted for. And they do that with a technique called titration.
The process itself is really elegant. You just take your water sample, you add an indicator that turns it a certain color, and then, very slowly, you add another chemical, the titrant, drop by drop. The second the color instantly changes, you stop. The amount of that titrant you use tells you exactly how much of that invisible impurity was in the water. It's all about precision.
Okay, so the water's been checked and verified. Now it's time for the backbone of the mud, bentonite. This is this super absorbent clay that just swells up in water. It's what gives the mud its gel-like structure and viscosity, or, its thickness. And that's what lets the mud carry all those rock cuttings back up to the surface.
And right here, we see exactly how they make sure the clay is up to spec. This page from the notebook outlines something called the methylene blue test, or MBT. It's basically a way to measure how well the bentonite can create that essential gel structure. A bad batch of clay could mess up the whole well, so this test is a huge deal.
So once we have our base gel, the next critical job is to handle that massive pressure coming from deep underground. And really, the only way to do that is to make our drilling fluid heavy enough to literally push back.
The special ingredient for this job is barite. It's a really dense, non-reactive mineral that's ground into the super fine powder. When you mix it into the mud, you're just making the whole fluid heavier. And that added weight, that density, creates what's called hydrostatic pressure that keeps the oil and gas safely down in the rock formation.
And just like everything else, the barite has to be tested. This page from the notebook shows what they call a rapid inspection process. Basically, they mix a very precise test batch with the new barite, and then they check its performance against a super strict set of targets.
And it really all comes down to this number. The final density has to be 2.30 grams per cubic centimeter or higher. If it doesn't hit that target, the barite just isn't dense enough, and the whole shipment gets rejected. It's a simple pass-fail test, but it has enormous safety implications.
But it's not just about weight. The barite can't mess up the mud's ability to flow. These targets for things like viscosity, its thickness, and yield point, which is the energy it takes to get the mud moving, are absolutely vital. They have to make sure the mud is fluid enough to pump, but still thick enough to carry cuttings. It's a really delicate balancing act, and it's all verified right there in the lab.
Okay, so this is where the chemistry gets really high-tech. Once the basic properties are set, technicians start adding a whole range of polymers to fine-tune the mud for the specific challenges of whatever rock formation they're drilling through.
These notes here show a test for a polymer called PHPA. This additive is fascinating. It actually does two things at once. First, it increases the viscosity, but more importantly, it coats the walls of the wellbore. This coating acts like a shield, and it stops sensitive clays and shales from swelling up and collapsing into the hole.
And here's another great example. The notes mention something called FLC, which stands for Fluid Loss Control. See, some rock formations are really porous, and they can literally suck the water right out of your mud. That leaves you with this thick, useless paste. So FLC polymers plaster the wall of the well and create a seal that keeps the liquid in the system where it belongs.
Now, these polymers have to perform under some incredible stress. We're talking high temperatures, high pressures, and all kinds of different water chemistry. So how can you be sure they'll actually work down there? You guessed it, you test them relentlessly.
Just look at these lab results for another additive, the XCD polymer. The fire readings you see in that table are just a direct measure of the mud's thickness at different speeds. But look, notice how the numbers are practically identical for both freshwater and saltwater. This is what proves the polymer is robust and reliable. It performs consistently no matter what conditions you throw at it.
So let's bring this all together. We've seen how every single component, from the water and the clay to the weighting agents and these specialty polymers, is individually tested and verified before it ever makes it into the final mix.
This quote from a procedure testing salts, it really captures the entire philosophy behind all this work. The goal is to make sure that the industrial-grade materials you buy by the ton perform exactly like the pure, perfect sample from a lab. It is all about consistency and quality control.
So the key takeaway here is this. Drilling mud is not just dirt and water. It's a complex, multi-component fluid system. Every single ingredient is chosen for a specific reason, and every batch is tested to make sure it can withstand the absolutely hellish environment deep inside the earth.
It makes you wonder, doesn't it? If this much science and this much precision is hiding in what looks like a bucket of mud, what other incredible feats of chemical engineering are hidden all around us in plain sight, just waiting to be understood?